Hello, pre-calc, and welcome to day 7. Here's the do now. Go ahead and hit pause while you finish this, finding the expected value for how much you'd win if you get to roll the die, and you get $2 times whatever number you roll. Okay, so hopefully we end up with an expected value of 7. All of our outcomes here, multiply each of those by 2 to get the dollar amounts. Frequency of 1, each of those numbers only shows up one time on each of the different sides of the die. Product is the value times the frequency, 2, 4, 6, 8, 10, 12. Total the frequency column to get 6, total the product column to get 42. Divide for expected value. Hey, so today we're looking at variance and standard deviation, both of which are some very important calculations in the world of statistics. Our learning target is that you'll be able to calculate those two quantities. So last week we took a pop quiz about Gilder, fictional kingdom. No questions. You had to randomly guess. I tabulated the results as shown here in this histogram. And so we calculated, before we even did the pop quiz, we calculated the expected value was 4. There's 20 questions. Each question, 5 options. If you're guessing randomly, you probably get 1 out of every 5 questions right, which is 4. So that's the mean. We calculated it as the mean. In the histogram, we can also see the mode is 4. That was the most common number of questions that you got correct on your version of the pop quiz. So both the mean and the mode are 4. And in the world of statistics, a lot of times large data sets are summarized, and just we use a measure of center as a summary, like mean, median, or mode are very common. You've probably learned all of those before. Those are all measures of center. We also have some measures of spread. So we want to know how far all of the different numbers on the histogram there are spread out. So the range is probably the most simple of all of the measures of spread. That's just the biggest number minus the smallest. So answers that people actually got, the highest number correct was 10, the lowest was 0, so we'd get a range of 10. Okay, but sometimes those summary measures are really not adequate at describing what's going on in graphs. So here's 2 different graphs. On the left-hand side, here's a graph for our class with a mean of 10 and a range of, a mean of 4 and a range of 10. And here's a different class. Let's say the class next door did the same thing, and this is a histogram of what they got, which also has a mean of 4, also has a mode of 4, and the range of 10. But we can see that these 2 graphs show some pretty different shapes going on. In our class, most of these students were in this central range, 3, 4, or 5 questions correct. Not so much if you get further out towards either the left or the right edge. But in this other class, you can see that there's a pretty wide band where people got different numbers correct, from 0, 1, 2, 3, 4, 5, 6, all the way up to 7. It's pretty high frequency for all of those. And so that gives the graphs a very different shape. If we were to randomly choose one person out of our class, most likely we would end up someplace right here in the center, 3, 4, 5 questions correct. If we randomly chose someone out of that whole group from the other class, it could be pretty much almost equally likely that they would have any of these different numbers of questions correct, right? So although there are some similarities, there are also some very important differences. And if we're summarizing just to these 2 numbers, the mean and the range, then it really doesn't capture all the other stuff that's going on, which is why statisticians don't just rely on the mean and the range. Particularly with the measures of spread, there are some other options that are far, far more useful and more important than the range. So one option that exists is to say, look, we need to find out how far away from the mean value right there in the middle, how far away from the mean is each of these data points on average. Okay, and so that's in the big red circle there. If we were to take any given data point, so let's just say the person that got 10 answers correct, then we'd subtract to find the distance from that data point from the mean. So 10 is 6 spaces away from 4. And I would continue that for every single one of those different data points represented in the histogram, and then average all of them to find the average spread. How far is each data point from the mean on average? Okay, and so we'd only want those to be positive because we just want to know how far spread out it is. We don't want to call the left side negative and the right side positive and have to worry about like, oh, well, if there's some over here that are positive and an equal number over there that are negative, those are going to cancel out and give us like our measure of spread would be like 0. And that would not be true because we have some on both sides. So we only want these distances to be positive numbers. Otherwise, you've got the positives and negatives that cancel. And we don't want that. Okay, so this idea is actually the mean absolute deviation, which is one of the things we're going to talk about today. So let's jump over here to some vocabulary. We've got 4 definitions we'll look at here, and these are all in the written notes, so you can write these down later. Mean, for our purposes, we're going to get that by doing the expected value. So in statistics, these calculations often have not only a name, but also a special symbol that they're referred to. And so the symbol for mean is X bar. Okay, mean absolute deviation is the second measure of spread, which is going to show up today. And it's not part of the learning target, but it is the critical step on the process to get there. This is that calculation which I just outlined a minute ago. If we take each of the data points, subtract to find its distance from the mean, and then after we've done that for all of the data points, we average it together. Okay, it's the average of the absolute value of the difference between the outcome and the expected value. And by doing the absolute value, that guarantees that we will always get a positive distance, a positive difference. We take our data point and the mean, we subtract to the absolute value, so it's always going to be positive. Okay, so this sounds like a great idea, and it works, you know, it does its job. But there's a lot of things that you can't do with a mean absolute deviation, and so statisticians really don't use it very often because it has these drawbacks. And so instead, another option to guarantee that we always have a positive distance is, instead of doing the absolute value of those differences, we could square each of those differences. So the next one up here is mean squared deviation, which is commonly referred to as the variance. Its symbol is the lowercase Greek letter sigma squared, because we are going to square. It's exactly the same thing as the mean absolute deviation, with this one difference. Instead of doing the absolute value of that difference, we're going to square the difference instead. Okay, well, the problem with squaring numbers is that kind of distorts them, right? Because now if you've got a number larger than 1, you square it, now it's a way bigger number. And if you had a number less than 1, like a decimal, when you square it, now it's way smaller. And so it's distorting those distances away from the mean because we're squaring it. And so that is not ideal. All right, so the last step in the process of our vocabulary journey here is at the root mean squared deviation, which is the big name, and some people don't usually call it that. They say, well, this is the standard deviation, because this is the standard type of deviation that is used. There's all these 3 different deviations here, and those other ones are, you know, they have their place, but this is the one that sets the standard. This is the one that people use. So this is the square root of the variance. So the square root right there, that is the difference between the red definition and the blue one. We have done the square root of the variance. Again, that's actually how we're going to calculate standard deviation, is by first finding the variance and then square rooting it. Okay, so to recap, all 3 of these last 3 vocabulary terms, the mean absolute deviation, variance, standard deviation, all of those are ways to measure how spread out the outcomes are in a particular data set, how far away from the mean or the center value. All right, now it is time to look at how to do these calculations. And so we're going to use a 4-column table. It looks just like the 4-column table that we have been using to find expected value. It even has the same first column where we're going to list the outcomes. That's the place where the similarities end. So everything else is different. The second column, we're going to calculate the mean absolute deviation. Third column will be the variance, and the fourth column is our standard deviation. So the bottom of each column, we're going to average all of the numbers in the column above that. So the first column, we have the outcomes. We're going to use the same outcomes that we saw in the do now. It's the values from the do now, but we're listing them here as outcomes. You could win $2, $4, $6, $8, $10, $12 from that dice game. Okay, add all of those numbers up and divide by 6 to get the average. You already did that as part of the do now, so we know that average is 7. Next column, mean absolute deviation. So in this column, we're going to subtract the mean and each of those different outcomes. We'll just do one at a time. So I'm going to subtract 7 minus 2, that's the first outcome, which is 5. I'm going to show my work. You don't have to show your work, otherwise I just want to make it clear for you what's going on. So 7 minus 4, that's 3. 7 minus 6, that's 1. Okay, and I do a little mental trick here. Instead of actually writing down absolute value every time, which really is what we're supposed to be doing, I just set my subtraction problem up so that I always get a positive answer. So at the next step, instead of saying 7 minus 8, which would give me a negative difference, I'm just going to switch the order of my subtraction so that I always get a positive answer, which is really accomplishing the same thing. But like, if you're going to write a definition, you don't say like always set the order of your subtraction up so that you get a positive answer. It's like, no. So I'm accomplishing the same thing. I'm just doing it kind of my own way here. So 12 minus 7 is 5. All right, so these numbers right here, those are the numbers that really I need to have in this column, those green highlighted ones. Average them. So I'm going to add all 6 of those numbers up, divide by 6 to get the average. And so 8, 9, 18. Those add up to 18. Divide by the 6 numbers in that column. 18 divided by 6 is 3. 3 is the mean absolute deviation. Next column, define the variance. This time, it's the mean squared deviation. That's the difference in the name between the variance and the mean absolute deviation. It tells us how we're going to do this differently. So I'm going to take this green highlighted number. I'm just going to square it. Oops, redder than green. So just do all of those in green. And I'm going to come back and square each of those. So this is 25, 3 squared is 9, 1 squared is 1, 1 squared again is 1, 3 squared is 9, and 5 squared is 25. At the end of each column, average. So I'm going to take those blue highlighted numbers right there, average them together. So 25 plus 9 plus 1 plus 1 plus 9 plus 25. Mental math. Adds up to make 70. Divide by 6 to get the average, and that is 11.66666, repeating forever. Awesome. Last column, standard deviation. Sorry. Circle that answer, the 11.666666, that is the variance. Now, moving on. Last column is standard deviation. To find the standard deviation, it is the root mean squared deviation, right? The whole rest of the name, the mean squared deviation part, that's the same as the blue one. All I need to do is take the square root of that blue variance. So I'm going to do the square root of 11.66, which is beep, boop, 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 beep, boop, beep. 3.41. That is the standard deviation. All right, so some similarities here between these two numbers. Those are pretty close in value, 3 and 3.41. Okay, so the reason why statisticians use the standard deviation is not that it's like some radically different number than we would have gotten from the mean absolute deviation, but that tiny amount of difference is really important because with the standard deviation, there's a whole host of additional things we can use it for in the world of statistics that you just can't use the mean absolute deviation for. So that's why we go through this process to get the standard deviation. So otherwise, you'd be like, man, that was a lot of extra work to get like basically the same number. What's up with that? Well, yeah, it's not a ton of work for no reason. There's a whole bunch of reasons, which we will learn in the next several days and weeks. All these different things that we use standard deviation in order to accomplish. So that is that.